Okay, let me officially begin my today's class. I will be discussing on cumulative distribution or distribution function, which I introduced in one of the earlier classes. Today I'm going to present a note which has been prepared. If board work is required, then only I'll go to the board work. Otherwise, there will be no board work from my end. Only if it is required, then I'll do. I will first, in the first session, I'm going to present this particular note, and I hope I will be able to explain what is written, the contents of the note. Okay. The first definition which is there, the definition has already been discussed in one of my earlier classes. This is the definition of distribution function in case of discrete random variable. Discrete random variables, to recapitulate the thing, random variable is a function whose domain is the sample space and whose range is the subset of set of real numbers. And discrete random variables means the function whose values are either finite or countably infinite. Then we say that this variable is discrete. Otherwise, it is continuous. Now, you already know that discrete random variable, if considered, its corresponding probabilities are calculated. And if we make a chart, that chart is called discrete probability distribution. And the probabilities associated with the discrete case is called a probability mass function. So we have assumed one such discrete random variable, which is denoted by capital X, and the distribution function is defined in the following way. We are denoting the distribution function by capital F. Now, capital F, whose value of the independent variable is small x. So the distribution function is defined as that function capital Fx, such that probability that the random variable capital X is always taking the values lesser than that value small x, which can be explicitly written with the help of summation. So we can write this particular thing with respect to summation sign by introducing one another variable t. T actually is a real number. That's why I have written that t is lying between minus infinity to plus infinity. But that doesn't mean that I'm considering the continuous case. I'm just saying that by writing this, I'm actually trying to say that t is a real number. I could have written that t is belonging to the set of real numbers. Now, since you have considered the discrete case, so the new variable t will take only the discrete values lesser than that small x, and their corresponding probabilities will be calculated and will be denoted by pt. We'll take those probabilities and together and we'll take their sum. Okay, where pt is the value of the probability distribution of capital X at small t. This type of function is called the distribution function, or sometimes it is called the cumulative distribution of capital X. Cumulative distribution is the same as cumulative frequency that you studied in a frequency distribution chapter earlier in school. The following theorem about the distribution function is very important, but the proof of the theorem is not required. The theorem goes like that: the values capital Fx of the distribution function of the random variable satisfy certain properties. F of minus infinity is 0, f of plus infinity is 1. What does that mean? Actually, minus infinity and plus infinity, these are actually considered to be an entity which is in abstract sense. Infinity, what is the shape of the infinity? Nobody knows. But at least we can say that this quantity, whatever its shape is, it's very large. It's too large, larger than we can imagine. Okay. To denote the positive abstract number, positive abstract largest number, we denote the plus infinity, and uh, to define a negative largest number, large number, we use the term minus infinity. But both of these plus infinity and minus infinity are not uh, part of the real numbers, because you see minus infinity, when I write t is a real number, what I'm writing? I'm writing t is lying between minus infinity and plus infinity. Equality symbol is not there. Or if you can recall that sometimes we write t belongs to open interval minus infinity to plus infinity. Okay, so minus infinity is actually not a real number. Plus infinity is not a real number, but any number between minus infinity and plus infinity is a real number. But if you consider an extended real number system, this extension, we call it extended real number, because in that case, we include minus infinity and plus infinity, and we consider the closed interval. So whenever I write t belonging to t is greater than or equal to minus infinity, and t is less than or equal to plus infinity, then actually I mean to say that I'm considering the extended real number system. So if we consider an extended real number system, these infinity and minus infinity becomes hypothetical abstract numbers, and distribution function at those points takes some values. At minus infinity, the distribution function's value is 0. At plus infinity, the distribution function's value is 1. I am taking a considerable amount of time to make you understand this, because since you are sitting for online examination, so this question will be asked, may be asked, I shouldn't say will be asked, may be asked, that what will be the value of the distribution function at minus infinity and plus infinity. Then you have to remember that one value is 0 and the other value is 1 respectively. And if we consider any two real numbers, small a and small b, then distribution in such a manner that small a is equal to small b, then in that case, the distribution function at the point small a is same. It is quite obvious that it will be same as the distribution function at the point small b. But if the the value small a is less than the value small b, the number small b, then the distribution function at the point small a will be less than the distribution function at the point small b. And this will happen for any real values a and b. Here we are not considering minus infinity and plus infinity. Remember. So we have separated the two cases by putting numbers 1 and 2. And there is another theorem which is just the opposite of what has been stated over here in definition. In definition, you see, if you carefully observe, the probability distribution PT is known, and with the help of PT, we can find out the distribution function. But the theorem says that if the distribution function is known for certain points inside the real number system, if the distribution function is known, can we construct the probability distribution? So here, cumulative distribution given, we are going to find the probability distribution. And with the definition, the probability distribution was given, we are to find the cumulative distribution. And the theorem goes like this. If the range of the random variable capital X consists of values such that it maintains a sequence increasing order, x1 is less than x2, the next one is less than x3, and so on, then the probability function at the first value will be same as the distribution function at the first value. And probability function at any value xi will be the distribution function, the difference between the distribution function at the value xi and the distribution function at the value xi minus 1. And it is true for any I lying between 2, 3, and n. So these three things, the definition, the theorem 1 and theorem 2, although I have not numbered the theorems, let us consider this to be theorem 1 and theorem 2. I am asking all of you to remember this, to memorize this. for the sake of your examination. These are very important results. I'm going to consider this question. The question has been taken from John Freun's book. So I'm going to explain what is happening over here. This is a very good example, and one such a discussion of one such example will clarify the thing to you. Two socks are selected at random and removed in succession from a drawer containing 5 brown socks and 3 green socks. So total number of socks here is 8. There are 3 parts in the question. Number 1 is list the elements of the sample space and the corresponding probabilities. Define the random variable that denote the total number of brown socks selected. Okay, and find the distribution function of the random variable. This is part 3. Part 4 is extra. It's asking us to plot a graph of that situation. So we'll encounter this particular problem one by one sequentially. Now you know that in the very first class I had already told you that you cannot assign probabilities to events if the events are not known properly, and events will not be known properly if the sample space is not designed properly. If you do not have any complete idea about the sample space, then everything is impossible. Everything becomes impossible. So therefore, they have asked you to find the sample space first. Finding sample space means listing all the possible elements in it. Okay. So 8 socks are present in the basket. The total number of brown socks is 5. The total number of green socks is 3. Now we are interested in finding and you are supposed to draw 2 socks, one after another. And when nothing is mentioned about the drawing of the sample, then we'll always consider that the drawing has been done without replacement. Okay, if the drawing is done with replacement, then that will be mentioned in the question. So here we are considering, suppose that the drawing has been done without replacement. Okay, what are the possible set of elements, set of points we can find out here? Elements of the sample space will be of this form. The 2 socks drawn will be brown, the 2 socks drawn will be green, or one of the socks is brown, the other is green, one of the socks is green, the other is brown. Now, just to tell you one thing, I want to share one particular information with you. You may think that this is a very silly problem. This socks problem is a very silly problem, but this problem is actually very has some philosophical content in it, because in quantum mechanics, in quantum information theory, when Einstein was not in agreement with Schrödinger regarding his comment on quantum mechanics, or the incompleteness of quantum mechanics, Schrödinger was deliberately trying to convince Einstein that quantum mechanics is complete. Then many authors, many scientists, on their part, they tried to explain things in their own way. So there was a very beautiful paper called, the paper's called, titles is called the Bartleman socks, where the Professor Bartleman always comes to the college wearing socks of 2 different colors. Bartleman socks, you can search in Google. It's a very interesting paper, but only you can understand its philosophical content if you understand the Einstein's original paper. So this socks problem that is actually that the socks problem I'm dealing with is not a Bartleman socks problem, but seeing this particular event, that one sock is capital B and another of brown color and another sock is of green color, Okay, this by seeing these two elements in the sample, it reminded me of Bartleman socks. I can see Bartleman present in these two cells, and that's why I shared this information with you. Now let's get back to our system. So if the now we are actually supposed to calculate the probabilities of the scenario. Now if the two socks are brown, now you see the once a particular sock is drawn, then it is not being replaced. So the probability of drawing the first sock, the probability that the first drawn sock is brown is 5/8. Or you can write out of 5 brown socks, you are selecting one in 5C1 ways, which is indeed 5. And in total case, from the total sock, you can draw one sock in 8C1 ways, that is 8 ways, and therefore it is 5/8. Then you are putting this particular sock on the table and you are going to draw the another. Now, since the first sock has come out to be brown, the number of brown socks, the total number of socks have reduced. And the total number of sock is now 7, and the number of brown sock is 4. So we are, for the second scenario, we are writing the probability to be 4C1 by 7C1. Now the two drawings of socks are independent of one another, and we know that probability of two independent for the independent events capital A and capital B, the probability of A intersection B happening together, that A intersection B means the two events are happening together, the probability of that is 5/4. Sorry, probability of A intersection B is probability of A into probability of B, and therefore the probability 5/8 and the probability 4/7 has been multiplied, and we got 5/40. Okay, I am trying to look into the probability from axiomatic point of view. I'm not trying to look into the probability from combinatorics or a classical definition point of view. I'm trying to look at it at from axiomatic point of view. Okay. Similarly, for the brown and the green socks, and the green and the brown socks, and the green and the green socks, you can calculate their respective probabilities in the following manner. I'm not explaining this thing because you have already understood how it is being calculated. Next job is to define a random variable. So we have listed the elements, we have listed the probabilities. Now our job is to allocate a random variable, to define a random variable on the system. Now the random variable which is being defined, according to them, it should be the total number of brown socks selected. It could have been the total number of green socks selected, whatever. In various ways, your random variable can be defined. According to the question, if I denote the random variable by W, you find that in the first element of the sample space, the total number of brown sock is 2. So W has got the value 2. And total number of brown sock in the second and third is 1. Total number of brown sock in the third is in the fourth case is 0. And why have I written small w in between? It's because to make you understand that capital W is the mother variable. Small w is one of the values of the mother variable. So capital W in the first case, taking the small w with value 2, capital W in the last case, taking the small w with value 0, and so on. So you see, capital W can be considered to be a random variable because it is a function from this sample space to that subset of set of real numbers, and that subset is taking in it 3 different real numbers only. They are finite and discrete. It's called 0, 1, and 2. So this random variable, since it is finite, it is containing finite number of values. Therefore, it is a discrete random variable. I hope you have understood and I'm able to explain everything to you. Now, Once we design this sample space, we have got our probabilities, we have got our random variables. So we shall now, in the next chart, we are going to write the random variables only and the probabilities only, because this the table where I'm moving my cursor, this table is not the probability distribution. In probability distribution, you are only supposed to write the random variable along with the probabilities. So actual probability distribution is the second one. So capital W is taking the value small 2. You know the probability is already 5 by 14. The capital W is taking value 1. The probability is 15 by 8. The capital W taking the value 0. The probability is 3 by 28. How are we getting W equals to 1 as 15 by 28? Because you see, W equal to 1 can happen in this case or in this case. Okay. So probability of W equal to 1 can happen in two different ways, either this way or that way. So probability of W equals to 1 will be probability of BG union GB. And BG and GB, they are mutually exclusive. So probability of BG union GB, that will be probability of BG plus probability of GB, which is twice 15 by 56, that is 15 by 28. Okay, here also I have used the axiom 3 of the probability theory. And once you find all the probabilities here, you are going to take the summation of, you are going to take the summation of all the probabilities. And if the summation comes out to be 1, then it means your probability chart is a complete chart. Okay, so we have tabulated all the probabilities here, and these individual probabilities which have been calculated, this 5 by 14, this 15 by 28, this 3 by 28, they are actually the values of the probability mass function, because we know that probability is associated with a discrete random variable is called the probability mass function. We can define probability we can denote probability mass function by either by this symbol or that symbol. Okay. Now, in the part C, we are going to calculate the distribution function corresponding to the given probability chart which you have designed. Now, try to recall the definition of the distribution function. It was probability of fx is equal to probability of capital X less than or equal to small x. And here it was written t less than or equal to small x. But since we have considered the random variable, we have denoted the random variable by capital W. So all the x's have been replaced by capital W's. So I have first written the definition over here. So it's f of W is equal to probability of capital W less than or equal to small w, and this, and so on. Here also remember, t is not a continuous case. I'm just saying that t is a real number. Now, one by one, we are going to calculate the values of the distribution function at different points, 0, 1, and 2. Because 0, 1, and 2, these are the only finite values of the random variable. Try to apply this definition over here. Let's see what happens. Capital F of 0, just look at this carefully, is equal to probability of x less than or equal to 0. Try to correlate these two things. By definition, it should be summation of pt, where t is taking the value 0, less or lesser than that. But since t is real number, but it is discrete, t can take only one value, which is 0. And therefore, I am writing here small p of 0. Small p of 0 is, from the chart, it is how much? 3 by 28. Just look at the chart. It is 3 by 28. Okay. Next comes capital F of 1. So again, we can write it as probability of x less than or equal to 1. Now, t can take value less than or equal to 1. Okay. But t is real number and discrete. So only two possible values are t equal to 0 and t equal to 1. So I'm writing here p0 plus p1. Now P0 from the chart, it is 3 by 28. and P1 on the chart, it is 15 by 28. If you add these figures, you will get 9 by 14. And lastly, when you put, try to find the distribution function at the point 2, so we are going to substitute 2 in place of W. So we are going to write it as probability of X less than or equal to 2. Now T can take only 3 values, possible discrete values, finite values, which are 0, 1, or 2. So that will be P0 plus P1 plus P2. And from the chart, if we take these values together, we will get 5 by 14, 15 by 28, 3 by 28. And the total probability is coming out as 1. Now this whenever I write X less than or equal to 2, that means X can take either 0 or X equal to 1 or X equal to 2. That means probability of X equal to 0 union X equal to 1 union X equal to 2 we are calculating. They are individually mutually exclusive, so we are adding these figures together. Remember that if your chart is complete, then the final value of the distribution function or the value of the distribution function at the final point must be equal to the total probability or sum of the probability mass function. If it is not 1, if this value is not coming as 1, that means your chart is not complete. That's how the statisticians often try to find whether the chart they are working with is complete or not. Now you can write all these values in a specific function because you know the functions are written. You already know, have done various such examples on functions in your earlier school days. Now I have here in this colored in this part I have only calculated the values, but the way it is written, it is not the way by which the functions are written. So functions must be written in a specific way. So right now, with the help of these values, these 3 values, 3 by 28, 9 by 14, and 1, I'm going to write the function in its actual appropriate form. So now let's see what I'm writing. My independent variable is not X, it is W. So I'm writing f of W. Now, since we are discussing about the zero, since we are discussing about the real number, now this W and this T, they are not dissimilar things. T is a real number, which I have this notation I have used, this particular notation to denote the real number I have used to calculate the things. Now W is also a real number, and T is actually taking different values of W at different points of time. Here T has taken the W's value, which is 0. Here T has taken 2 values of W, which is 0 and 1. Here T is taking 3 values of W, which is 0, 1, and 2. So do not make yourself confused, and do not be lost in this set of notations. Try to understand what the notations are actually trying to say. Now, apart from these 3 real numbers, 0, 1, and 2, there are many other real numbers actually, because real number set is infinite and uncountable. So what will happen to the distribution function when this variable 0, the variable W is taking value less than 0? Because less than 0, we can also consider discrete points, but we do not know that because that probability is not known to us. Okay, it's not there in the chart. So we have written that probability of the value of FW when W is less than 0 is 0, because we do not know it. When W is, now W can take, W is discrete, it is not continuous, but it is a real number. So if I say W is lying between 0 and 1, so you see that only one possible value is available, that is W equal to 0. Okay, because I am writing it in this manner because we know that we have to work within the limits of 0, 1, and 2. We cannot go below 0 and beyond 2. So if I write it in this manner, it is the way of writing it only. So W, only possible values for W is 0. And you know that in that case, the probability is how much? It is 3 by 28 calculated from here. So we have written 3 by 28 in this case. Now, the next case here, you try to see that 0 has been included in the system, but 1 has been excluded. Okay. Next case, the next phase, what you can do, you can include 1 and you can exclude 2. So if you does so, what are the possible values of W? Then W equals to 1. W equals to 1. W can take only one value here, 1. But according to the distribution functions, when this happens, then actually what do we get? You get it from here. Okay. And that becomes, whenever I am writing t less than or equal to 1, that means we consider t equal to 0 and t equal to 1. We got 9 by 14. Okay, so the previous result has been calculated with the current one to get the latest one. So when I am writing W equal to 1, that means the latest value has to be taken into consideration, which is 9 by 14. Okay, so we have written here 9 by 14. And when W is greater than or equal to 2, then we know the value is 1. It has to be, because distribution chart, the last value of distribution chart should be equal to the total probability. And the thing which we have calculated is actually in correspondence with the function we are designing. So our calculation is all right. The things will be more clear if I plot the distribution function in the following manner. So in this graph, on the horizontal axis, we have placed the variable W, and on the vertical axis, we have placed the function FW. Now look at the function. When W is less than 0, that means you are considering the negative side of the horizontal axis. Nothing is there, no points are there, no probability or distribution functions values are there. When W is lying between 0 and 1, you see that at the point W equal to 0, probability is 3 by 28. Distribution function is also a kind of probability, because it is the sum of, it is either the probability or the sum of that. So it is 3 by 28, and it remains 3 by 28 throughout. And at the point 1, it suddenly jumps to 9 by 14. So therefore, there is a dotted line present over here. Okay, then it remains as it is until it reaches 2, and it suddenly jumps to 1, and it remains throughout 1. It remains 1 throughout the remaining portion of the real number. So you see that distribution function is a kind of step function, and you have worked on step function many a times earlier in your school days. Okay, so distribution function is an example of a step function, one of the special cases of step function. So that is how we calculate the distribution function, and we try to plot them. Here in this particular example, I have shown you when a distribution function is calculated, how to find the probabilities of various other values. Say for example, that you see the distribution function is starting, the range of values which has been considered over here is from 1 to up to 10. When distribution function is when x is less than 1, distribution function is 0. When x is lying between this, it is 1/3, and so on. The last value is 1. So this question number 2 is exactly opposite of what we have calculated in the question number 1. Now they have asked you to calculate the probability. So here you are going to find the probabilities and probability distribution, just the opposite case of the previous one. So definitely you have understood that in this particular case, you are actually going to apply the theorem 2 of today's class. The theorem 2 is f of x1 is equal to capital F of x1 I have rewritten the theorem over here. By using this theorem, you can calculate the probabilities accordingly. I have shown here, I have tabulated all the possible values starting from 0 to 11. Okay. And I have started counting from 0. I have tabulated all the values here and all the discrete values, because at the end of the day, you have to keep in mind that we have not gone into the domain of the continuous function. We are only dealing with the discrete function. And from there, you can calculate the respective probabilities by using the above theorem. So Px1 is actually what? P0. And P0 is, since it is the first value, it should be equal to the value of the distribution function at 0, which is 0, which is 0. It is clear from the distribution function. Just have a look at the distribution function once again. Okay, I'll send you the note. Don't worry. And similarly, Px2 can be calculated. Px2 is P1. It will be calculated using this formula, that Pxi. Here I'm using the notation P instead of F. So don't get confused that in the theorem F was written. Now I'm writing P. Notations can be changed according to your wish. Okay. I am writing P because in the question they have mentioned capital P. So I didn't want to distort the system. So Fxi is capital Fxi minus Fxi minus 1. And by this rule, I have calculated the probability P1 as F1 minus F0, which is 1/3. And in this manner, all the respective probabilities have been calculated. Okay, till Px10, Px11, all the probabilities we have calculated. The probability distribution is therefore rewritten in the following manner. The P0 is 0, P1 is 1/3. Whatever we have calculated, I have put these things in the table. And once you get your probability in this manner, you can very well calculate the respective probabilities. Like when probability take the value x equal to 4, it is clear from the chart, it is 1/6. When x is taking value 2 between 2 and 6, it is P3 plus P4 plus P5 plus P6, and so on. So from the we have learned from the distribution function, very easily we can calculate the probability mass function, and we can calculate the different probabilities. Okay, and I have set one practice problem for you so that you can practice it by yourself. These parts will be explained later on. Don't worry, when you will get the note, you'll just have a look at this. You already know these results. Okay, so I'm stopping my recording and let's meet in the next session.